Welcome to the another video of the power quality. In this video, we will be learning from this numerical that single phase fully controlled bridge converter. A single phase fully controlled bridge converter where the supply is 220 volts and 50 hertz and the firing angle is meant as 60 degree and the load current is 10 ampere. IID is 10 ampere. So if we draw this one, here we have the supply voltage, single phase supply, and that is 220 volts, 50 hertz. And this we give it to the usually fed to the isolation transformer, and through the isolation transformer this goes to the single phase fully controlled bridge rectifier, which consists of 4 thyristors. So the AC supply is given inside, and here we have the load, and load is represented by a sink which carries 10 ampere of current. That means load is carrying a current of 10 ampere, and the thyristors T1, T2, T3, T4. So what is given is that alpha is the firing angle alpha is given as 60 degree. So if this is a situation, so what will be the output voltage will look like? Now here the output current is given, the output current, and I would like to draw the output current and the input current both together. So here if I draw the ID as the output current, it is a straight line of 10 ampere. And when I would like to draw the IS, the input current will be a square wave which alternates between ID and minus of ID. This will be obviously 2 pi and this is pi. In the x-axis, if I represent by omega t in radian per seconds, and here will be ID and this will be minus of ID. Now since the firing angle alpha is 60 degree, instead of starting from 0, it will not be starting from 0, rather it will be starting, this is pi and 2 pi, it will be starting at 60 degree, the waveform will start at 60 degree and again go back down and it will make the same pattern. So instead of starting from 0, it will be starting at 60 degree, and at steady state we will be getting this type of waveform. So the input current waveform is look like a square wave. The output current is a perfect sink DC of 10 ampere. The question is asked, what is the TSD of the AC main? That means what is the TSD, total harmonic distortion, at the AC supply side. The TSD is given as we know, total harmonic distortion is given as root over of Is square minus Is1 square divided by Is1 square. We can also understand the THD, total harmonic distortion, as if the Is is the total supply current and the fundamental is removed from it. So we can also say that this is Is2 square plus Is3 square plus Is4 square plus Is5 square and so on, divided by Is1 square and whole root over if we can also understand in this language. And since it is a square wave, it doesn't have the even harmonics, so this even harmonics terms I will just erase it out. So only the terms like IS3 square, IS5 square, and similarly IS7 square IS9 square, all those harmonic. In other way, TSD is the addition of all the harmonic square divided by the fundamental current square. That is, you are comparing with the fundamental current. We are explaining this because there is another question called distortion index of the AC main. What is this distortion index? The distortion index is harmonic power divided by the total power in the waveform itself. That means if TSD, if I can rewrite here, I can also represent the TSD as IS3 square, IS5 square, and so on divided by IS1. If I multiply this with IS1 divided by IS1 will cancel out. That means I am taking the ratio of all the harmonics, root over of sum of all the harmonics square divided by the total current IS. When I divide it by the total current IS, it is distortion index. And when I divide it by the fundamental current, it is THD. That's the difference between the TSD and the distortion index DIN. Okay, so what we need to know from right now is that what is the value of IS here. So what is the value of IS will be, we know from our experience that IS is the fundamental current. So IS is the, not fundamental current, IS is the current, this square wave, that is the, this is the IS, and the fundamental component of it that I can also represent it here, the fundamental component of this is IS1. So you can see that this fundamental component is, in this way it is changing, and this is what is called IS1. So IS is the RMS value of this square wave, and that is obviously, since it is changing from 10 to minus 10, so the RMS value is also 10 ampere. That we have seen in the other problem. If it is a square wave, the RMS current is 10 ampere. And what is the value of IS1? IS1 is 4 ID by pi. In other sense, this is 0.9 times of ID, or I can write this is 9 ampere. So IS1 is 9 ampere, IS is 10 amperes, and then we can find what is the value of THD. So instead of writing all those things harmonic, so simply we can take the formula, this one, and write down that this is equals to 10 square minus 9 square divided by 9 square, and that comes out to be 0.4843, the TSD, and we can also say this is equivalent to 48.43%. So 0.4348 is the TSD over here. And suppose I would like to get what is the DIN, distortion index. So what I can take is that this is the TSD value. So, and this is what IS1 is 9, IS is 10 into the THD, that is 0.4843. So I can write 9 by 10 into 0.4843. That comes out to 0.4358. So that is 43.58%. So when I compare with the IS, this is the distortion index. When I compare with IS1, this is the THD. Okay. So next go to the another question. Total demand distortion of the AC main current. Total demand distortion of the AC main current. This is the total root sum square harmonic current distortion in percentage of the maximum demand load current. So it depends on the maximum demand load current. So this value of TDD will be equal to THD only, because it It is working on the rated value of the, we're talking about the total current of 10 ampere. So TDD will be equals to THD, and that is equals to 0.4843. That's the value of TDD. Next is what is the distortion factor, DF. So distortion factor, already we know this is the distortion factor, that IS1 by IS is the distortion factor, and we can write over here. So the distortion factor is equal to IS1 by IS, that is 9 by 10, that is 0.9. And another is, what is the displacement factor? Displacement factor is here, like this is the y-axis. So the fundamental component of the current, how much it is displaced from the zero line, that is giving you the displacement factor. This is the displacement factor talking about. The displacement factor is, I can write here, displacement factor will be equal to cos of alpha. Alpha is 60 degree here, so it is cos of 60 degree. That comes out to be 0.5. Now, what is the power factor? The power factor of the AC current, AC input current. The power factor of the AC input current is nothing but the distortion factor into displacement factor cos of alpha, and that will be nearly equals to 0.45. Now you can see that the power factor is 0.45. If we see from the waveform, anyone could like say that this power factor is cos of 60 degree, that is 0.5. But don't forget to multiply the distortion factor with the power factor, which will, with the displacement factor, that will give you the value of the power factor, 0.45. So this is how we solve this numerical on single phase fully controlled bridge converter, and we understand what the terminologies like distortion index, total demand distortion, and the other term like distortion factor, displacement factor, power factor, and also the TSD. We get a comparison between the TSD and the distortion index as well. Thank you very much.